Oh, good morning, student. Welcome to the class. I hope my voice is audible, right?
Good morning,
Good
sir.
morning, sir.
Good morning. Good morning. So, a quick recap on what we have seen yesterday. So, I told you there are three types of we classify materials into three categories: conductors, insulators, and semiconductors. And we are going to classify them based on what condition it is the forbidden energy gap, or you call it as band gap, energy band gap. Based on the energy band diagram, we are going to classify them. The parameter is called as forbidden energy gap. It is the energy gap between conduction band and valence band. For insulators, we have seen this energy band, this energy gap is very high. For semiconductors, it is approximately 1 electron volt. And for conductors, both the bands are overlapping. So I can say it is zero. The energy band gap is 0 electron volt. And we have seen in insulators how much ever energy you give, you cannot push the electrons to move from valence band to conduction band. So the conductivity is theoretically zero, or I can say it is having extremely poor conductivity. And the free electrons it has is very, very less, 10 power 7 electrons per meter cube. So then we come to metals. You know, in metals we have lot of free electrons because you have overlapping valence and conduction band. So whatever electron is there in valence band will go to conduction band. And in conduction band, if the electron needs to produce current, it has to move. It cannot move on its own. So you have to give additional external energy in the form of electric field. So if you apply electric field, then the electrons will go into the highest level of conduction band and they will start moving and you get what is called as current. And you have one term in conductors called as drift velocity. It is the velocity with which electrons are moving when you are going to apply an electric field. So drift velocity is proportional to the electric field. And the constant of proportionality we have seen, it is equal to mobility mu. So mobility refers to the how fast the electrons are moving. Mobility and velocity are not same. Okay, velocity, you know, it is distance traveled by time taken. Mobility is because of applying electric field, how much electron the or what is the capacity of electron to move, whether it is moving faster or it is moving slower because of the applied electric field. Okay, so this movement of electrons itself constitutes current. And you have the expression for J. See, whenever you are going to use a two-dimensional conductor, it is going to have an area. So there you will be using the term J. J is called as current density. So the formula for J is equal to number of electrons into the charge into the drift velocity, NQVD. We substitute for VD is mu into E. And we know that NQ mu is going to be sigma. Sigma is going to be the conductivity. So know these two relations. We'll be using them very frequently in semiconductors. So J is equal to sigma E is one relation. Sigma is equal to NQ mu is one relation. Sigma is the conductivity. N is the number of free electron. Q, you know, charge of electron 1.6 in 10 power minus 19 coulomb, and mu is called as the mobility. And you see in metals, you have large number of free electrons, 10 power 28 electrons per meter cube. So that is the reason why metals will conduct even when you apply the slightest amount of energy. Okay, the conduction happens when you apply the slightest amount of energy. So now, any doubt in yesterday's question? So we have just quickly recapped what is seen yesterday. I hope please daily you download the PPT and have a look. Just glance through daily what is happening in the class so that you will be clear on what is going on. You will also be conceptually strong. So having studied about metals and insulators, now we are going into the topic of our interest called as semiconductors. So semiconductors, as the name indicates, they fall between conductors and insulators. So definitely number of free electrons will be between the two numbers. For insulator, it's 10 power 7. For conductor, it is 10 power 28. So for a semiconductor, the number of free electrons will be between the two ranges, 10 power 7 and 10 power 28 electrons per meter cube. Okay. And you know, we have seen in the energy band diagram, it has a band gap energy of 1 electron volt. And remember, throughout your course, 4-year course of PEC, you will be traveling with these two terms, silicon and germanium. So the two popularly used semiconductor materials are germanium denoted by GE and silicon denoted by SI. Silicon, you see, silicon is nothing but sand. You go to beach, you see a lot of sand, right? That is nothing but silica. So once you purify that sand and then use it, that is going to be the purified form of silica. So silicon is nothing but sand. Okay. And see the energy band gap of silicon and germanium. Germanium has an energy band gap of 0.785 electron volt, and silicon has a band gap of 1.21 electron volt. So that's what we said. It is around 1 electron volt. So slightly less than 1 electron volt is the band gap energy of germanium. Slightly more than 1 electron volt is the band gap energy of silicon. And everything is at 0 degree Kelvin. So this energy band gap is at 0 degree Kelvin. Okay. So understand that the average band gap of semiconductor materials, whatever is available, the average band gap is going to be 1 electron volt. It will not be exactly one. It will be slightly more than one or slightly less than one. We are more bothered about silicon and germanium because they are widely used semiconductor materials in our electronics and communication domain. So at low temperature, the valence band is full. See the band gap. This condition is 0 degree. 0 degree is a very low temperature, right? 0 degree Kelvin means minus 273 degrees Celsius. So at low temperatures, the valence band is full, conduction band is empty. So conduction band is empty means there are no free electrons in the conduction band. So when the conduction band is empty, no electrons, no current. So they can be considered as insulators. At low temperatures, these semiconductors work as insulators. So you cannot expect current out of a semiconductor at low temperature. Okay. When you increase the temperature only, they start conducting. See here, when the temperature is increased, the conductivity will increase, and that is why they are called as intrinsic semiconductors. Okay. So at low temperature, you cannot expect the semiconductor to operate and it will not produce current. At slightly increased temperature, only they will start working. So what happens when the temperature is increased? When the temperature is increased, some of the electrons in valence band will acquire this energy and they will move into the conduction band. Now in the conduction band, the electrons are free enough to move. So the electrons will be freely moving in the conduction band, giving rise to current. So remember, at low temperature, the energy is not sufficient for the electrons to go to conduction band. So when you increase the temperature, when you use the semiconductors at room temperature, these electrons will acquire the energy from the room temperature and they will start moving into conduction band. So once the electrons are in conduction band, they can move freely, giving rise to current. So these three electrons are called as conduction electrons, constitute for conduction, and the material becomes slightly conducting. So when you see the semiconductor, everything depends on temperature only. So the temperature is more means the conductivity is also going to be very, very high. At low temperature, the conductivity is going to be almost zero. Now see, so we are going to denote the current density J. Usually we have seen conductors J is equal to sigma E. But here I'm denoting it as Jn. Jn equal to sigma N into E. Why Jn? This N indicates your electrons. Okay. N indicates your electrons. So Jn equal to same formula, sigma N into E. All other things will be same. This mu will be N because electrons have separate mobility. Okay. So see here, similarly, when you have electrons in conduction band, all the electrons from valence band has gone to conduction band, right? So there is absence of electrons in the valence band. So that absence of electron is called as hole. See, you should have studied about a particle called hole. Hole is not physically present. Remember that electron is physically present. But when electron is going to move from one place to another, the absence of electron is going to be treated as a hole. So assume electron is at point A. Okay. And you have 2 points, A and B. Okay. So assume electron is moving from point A to B. Okay. When electron is moving from point A to B, at A, the electron is not there. So at A, you will have a hole. At B, since you have an electron there, this B will have an electron. So whenever an electron is moving, that position is becoming absence of electron. That is going to be called as hole. whole in a physical particle, the whole is logically not existing. Absence of electron is going to be considered as a whole. Okay, so in conduction band, you have a lot of electrons. These electrons have come from valence band. Okay, so in valence band, you will have these holes available in the valence band. And these poles also, just like electrons, they are positively charged, but electron is negatively charged. This hole is positively charged. And even these poles also start moving, giving rise to what is called as hole conduction current density. So see here, previously I used Jn. Jn is for the current density because of electrons. Now, since your holes are also there in the valence band, you have one more current density called as Jp. So Jp is for the hole. P indicate your hole. See, everything is same. Here, in wherever you have n, you have to put p. So Jn equal to n into mu n into q into e. It is sigma n into e. What should be Jp? Jp is equal to p into mu p into q into e. So p into mu p into q is going to be sigma p. So Jp equal to sigma p into e. So you see that the mobility of electron is different. It is given by mu n. The mobility of hole is different, given by mu p. So those both electrons and holes will not move with the same mobility. The electron will move faster compared to hole. And n is the number of electron, p is the number of holes. So everything is same. Okay. Now in semiconductor, remember you have conduction because of electron as well as hole. So both electrons and holes will constitute to what is called as the total current. So total current density J is given by add both. So J is going to be Jn plus Jp. What is Jn? N into mu n into q into e plus n p into mu p into q into e. Q into e is common. Take it outside. So you get n into mu n plus p into mu p into QE. And I know that J is equal to sigma E. So this entire term becomes equal to sigma. So in semiconductors, very, very, very important thing, the conductivity will depend on electrons and holes. See here, sigma, the expression for sigma, you see, it is n into mu n plus p into mu p, whole thing multiplied by q. The conductivity depends on n. N is number of electrons. Conductivity depends on p. P is the number of holes. Okay, so it depends on when the semiconductor is going to be pure. You are not going to add any impurity. It is going to be pure. Then the number of electrons and holes will be same. And that I'm going to equate that by Ni equal to N equal to P. So for this condition is only for a pure semiconductor. When the semiconductor is going to be a pure semiconductor without any impurities, number of electrons will be equal to number of holes. So N will be equal to P. I am using a common variable Ni. Ni indicates the intrinsic carrier density. Intrinsic means pure. Remember, intrinsic pure. So if you replace n is equal to p, I can take this from this term, I can take n and p are same, so I can take it outside. So my final expression for j becomes j is equal to ni into mu n plus mu p into qe. So this is the current density for a semiconductor. Okay, so any doubts you have so far? We have seen the properties of semiconductor. Any doubts you have, you can ask. I'm giving a few seconds for you to ask any doubts in the topics we have seen so far in the today's class. Are things clear?
Yes, sir.
Okay, semiconductors, remember two important points. One is temperature will increase their conductivity. First point. Second point, conductivity depends on electrons and holes. Very, very important thing. But in conductors, we didn't use any term called Jn or Jp, right? We use only J because electrons are dominating there. You have lot of free electrons. Okay, electrons are dominating there, and there is no hole there because electrons in valence band will directly move to conduction band because both the bands are overlapping. So அங்க வந்து ஹோலுங்கிற கான்செப்டே கிடையாது. But in semiconductors, since only after applying some energy, electrons from conduction valence band are moving to conduction band, right? So in that case, the absence of electrons will give rise to what is called as hole. And this hole will also play an important role in the conductivity of your semiconductor. Please be very clear on that. Okay. So how will what all the different semiconductors we are using practically? See here, all the one common similarity all semiconductors have is everybody is having crystalline structure. You have a proper crystal structure for all the semiconductors, and we are using germanium, silicon. We have seen, and one more thing, we are using gallium arsenide. This also used in applications. I think you have heard about LEDs, right? Have you heard about LEDs? Can anybody
Yes,
say what is an LED? What is an LED? You have seen LEDs, you are seeing LEDs daily. What can anybody expand LED? Have you come across the term LED?
light emitting
Light
diode.
emitting diode.
Light emitting diode. What does can anybody knows how does it works? If you give energy, it will produce light. Simple, right? It is also a semiconductor only. So gallium arsenide is a semiconductor used for LEDs. But silicon and germanium cannot be used for LEDs because when you bias silicon and germanium, they only produce current and they don't produce light. But gallium arsenide, because of its unique band structure, when it is going to be driven by energy, it is going to produce photons. It is not going to produce current, it is going to produce photons. So silicon and germanium are used in normal diodes. Gallium arsenide is used in light emitting diodes. So maybe LEDs, I think we have it in our syllabus also. Maybe when I teach LEDs, that time we will remember, we will be coming across this term very frequently, gallium arsenide. Okay. So among the three, we are going to focus on germanium and silicon only. Okay, and the band gap energy. So the energy required for releasing electron from valence band is 0.66 for germanium, 1.08 electron volt for silicon. It is 1.58 electron volt for gallium arsenide. So germanium is relatively more pure and it can be crystallized easily. So germanium is earth. Where is germanium obtained? Germanium is an earth element and it is obtained from the ash of certain coals or from the flow dust of zinc smelters. So germanium is a relatively rare metal, rare earth element, and it is obtained from the ash of coals. Silicon, it is available abundantly in the form of sand. Okay, silicon is available in the form of sand. So silicon is abundantly available, but germanium, relatively, it is going to be tough to get germanium. And whatever germanium you get will be in the form of germanium dioxide only. And from germanium dioxide, you have to remove the oxygen and make it germanium. So that is called as reduction. Oxidation and reduction, right? So when you remove oxidation, the process is called as reduction. So germanium dioxide is available in nature. So from germanium dioxide, if you want to if you want to produce germanium, you want to reduce the reduction process and convert germanium dioxide into germanium. And germanium is very mostly used semiconductor because it has a very narrow band gap, 0.66 electron volt only. But silicon, it is almost 1.1 electron volt, right? So because of this low energy band gap available in germanium, it is used in many fiber optics communication system equipments. And silicon, it is found in common rocks. Sand is silicon dioxide. So sand is SiO2. So if I want to get silicon from SiO2, here also I should go for reduction. So if I remove that oxygen, it becomes silicon. So we get silicon from silicon dioxide. Silicon dioxide is also a natural insulator. You know that all semiconductors are insulators only by default. Only when you increase the temperature, they act like semiconductors. So remember that. And silicon is mostly preferred over germanium because it has a large energy gap, which helps the devices to operate at high temperatures. Okay, so since the energy gap is very high, devices made of silicon can operate at a very high temperature compared to germanium. And also, silicon is a better thermal conductor. Okay, it can conduct the better compared to germanium. And when you see gallium arsenide, it has a very high electron mobility, which leads to faster switching capabilities. So the gallium arsenide also, you see, it is 1.58 electron volt energy band gap. So it can also help in operating the device at a very high temperatures. Okay, so we will be seeing all the three elements, but we will restrict our study only to silicon and germanium. Okay, so germanium available as germanium dioxide. If you reduce it, you get germanium. Silicon is also available as silicon dioxide. If you reduce it, you will get silicon. And we prefer silicon over germanium because the band gap is high. So if the band gap is high, you can operate at high temperature. That is the logic. So among the three, gallium arsenide provides the highest operating temperature. Silicon comes next. Germanium comes third. Okay. And now we will go deep into semiconductors. We will go deep into semiconductors and see what are the types of semiconductors. So semiconductors are classified into two types, intrinsic and extrinsic. Intrinsic, as we have already come across this term, intrinsic. Intrinsic means pure. The semiconductor is pure. So when the semiconductor is pure, it will not conduct, it will act like an insulator. Okay, when the semiconductor is pure, it will act like an insulator. Extrinsic means impure. Impure means I am going to mix something and make the semiconductor impure. So intrinsic pure, extrinsic impure. Okay, so when the semiconductor is intrinsic, what happens even at room temperature, some of the valence band electrons will go to conduction band and constitute current, but this current is not very large. Okay, because the characteristic of a pure semiconductor is an insulator. So all pure semiconductors behave as insulators ideally. Only when you increase the temperature, they will slightly start conducting. So pure semiconductor is not often preferred because the conductivity is poor even when you provide energy. So see here, when you have an electron in valence band, when it's moved to conduction band, the absence of electron, you will have a hole here, and the electron is available here. So conduction band will have a lot of electrons, valence band will have a lot of holes. This is called as creation of electron hole pair. So when is this creation of electron hole pair happens? When you provide energy. When you provide energy which is exactly equal to the band gap energy, one electron from valence band moves to conduction band. An electron is going to move from valence band to conduction band. Absence of electron in valence band gives rise to what is called as hole. Sometimes you denote hole by this symbol. You put a plus and round it, or you put a dot and round it. So anyway, you can denote a hole. So the conclusion is intrinsic semiconductors are not fit for use because the conductivity is very, very poor at room temperature. Okay, so that is what is said here. So whenever an electron is moving from valence band to conduction band, you will have a hole. And in intrinsic semiconductor, you will have electrons in conduction band and you will have holes in the valence band. And total current is going to be sum of the current due to electron plus sum of plus the current due to holes. So the total current is due to the free electrons and holes, which is measured in the external system. This is going to be the intrinsic semiconductors. The holes are positively charged, right? So they will move towards the negative end of your battery, and electrons are negatively charged, so they will run towards the positive end of the battery. So when this happens, this is going to be contributing the current flow. So actual direction of current flow is the direction of holes only. So this is the actual direction of current flow. The action or the direction of electronic flow is this one. So I told you yesterday, right? So direction of current flow of electrons and holes will be opposite in direction. Holes will move towards the negative end of the batteries. They will move in anti-clockwise direction. Electrons will be attracted towards the positive end of the battery. They will be moving in clockwise direction, and you see that both directions are completely opposites. Okay, but we always refer to the direction of current is going to be the opposite direction of the hole, now our direction of the electron. So current will always be assumed to flow away from the battery, but actual electronic current will be flowing in the opposite direction. Be very clear on that. Okay, so when I'm going to give some energy to semiconductor, this movement of electrons and holes will take place. Holes will be moving towards the negative of your battery, and electrons will be moving towards the positive of the battery. So you will have two currents. One is current due to electron, another one is current due to hole. So total current will be equal to current due to electron plus current due to hole. This process is called as drifting. So drifting means getting attracted towards the opposite charge, moving fast. This is called as drifting. Holes will be drifted towards the negative end of battery, and the electrons will be drifted towards the positive end of battery. When the battery is not there, they will be lying as it is. When you connect the battery, this drifting happens instantly. So because of the energy you supply, and the semiconductor is also very pure, right? So you cannot expect very high current produced from the semiconductor. So even though electrons and holes are moving and producing current, the current is not sufficient for me to run an application. That is the reason why I don't prefer intrinsic semiconductors. So what it leads to? It leads to what is called as extrinsic semiconductors. So I'm going to make the semiconductors impure by adding some elements. Okay, so we are going to see what is extrinsic semiconductors. Any doubt? Anybody is having an intrinsic semiconductors? You can ask. Please interact and ensure that whatever you learn is completely free of doubts and clarifications. So at the end of the day, when you have learned something, you should be very confident in that. You should not have some doubt always when you learn some concepts. Any doubt at any point, please, you can ask me. These are basics, and you need deep understanding, because everywhere we'll be coming across these terms: intrinsic, extrinsic. We'll be frequently coming across these terms. At that time, if you don't know what is intrinsic, then understanding becomes difficult, right? So remember, intrinsic is pure. An intrinsic semiconductor also going to conduct and produce current. But what is the drawback? The current produced is very low because of the purity of the semiconductor. Okay, so we go to extrinsic semiconductor. Why we go to extrinsic semiconductor? The reason you know, because the intrinsic semiconductors have poor conduction at room temperature. So I want to increase the conductivity. So if I want to increase the conductivity, I am going to add some amount of impurity to the intrinsic semiconductor. So intrinsic semiconductor is going to be the purest one. If I'm going to add impurity, that intrinsic conductor becomes impure, or it is called as extrinsic semiconductor. Okay, so intrinsic is pure, extrinsic is opposite of that, it is going to be impure. So the process of adding the impurity is called as doping. So remember, this term doping also will be coming very frequently across the subject. So doping means what impurity I am going to add to an intrinsic semiconductor to make it an extrinsic semiconductor. So I will not be adding any element randomly as I like. There are rules for doping. What element I should add, how many element I should add. So what element, if I add in what ratio, I'll be getting increased conductivity. See, the goal of going to extrinsic semiconductor is I want to increase my conductivity. So for that, what I'm doing, I am adding impurity. See, then there is a saying, when something is pure, it is not usable, right? So you take 100% pure gold. When you have 100% pure gold, that is not useful in ornaments or any. It is not useful because it becomes very tender. You can even bend that gold. But only when you add impurity in the form of copper to that gold gets strength. That gold only is used for making ornaments or gold bars. Okay, so anything which is pure in nature, it will not be that much useful. That everything comes from nature, right? The intrinsic semiconductors are also very pure. That is why the conductivity is very poor. So if I want to increase the conductivity, just like what example I said in gold, if I want to make gold stronger, I need to add impurity in the form of copper. Okay, I need to add impurity in the form of copper. So that adding the impurity, that process is called as doping. Again, doping Yes, sorry for the interruption. So that how much doping I am going to do, that is going to be doping, and amount of impurity should be added extremely small. So you should not add too much of impurity which will disturb the element at all. So I cannot add the so much impurity to my semiconductor. Okay, so the amount of impurity how much I am adding is extremely small. So how much you see it? I am going to add only 1 to 2 atoms of 10 power 6 intrinsic atoms. So if you have 10 power 6 intrinsic silicon or germanium atom, I am going to add 1 to 2 atoms of the impurity. If you add more impurity, then the element will not work at all. So there is some specific ratio in adding the number of impurities. So be clear on that. So the process is called as doping. What is doping? Doping is the process of adding impurity to an intrinsic semiconductor to make it extrinsic. Why I am adding doping? To increase the conductivity. Can I add doping? Can I make doping random? No. There is some rule. I should add very small quantities of impurities. So 1 to 2 atoms of impurity only I can add for 10 power 6 intrinsic atoms of silicon or germanium. For example, if you have 10 lakh silicon atoms, I can add 1 or 2 impurity atoms. So see how much ratio the impurities are added. I am adding the impurity at a very lowest level. And now we are when I'm going to add impurity, two types of impurities are available in the nature. So first one is N type. Okay, first one is I'm going to add N type impurity. N means always indicate. Remember, N indicates electrons. Okay, when I'm going to add N type impurity, I am going to have excessive number of electrons. Okay, so see here, you have germanium, you have germanium, you have germanium, you have germanium, and this germanium atom is replaced by antimony. This Sb is called as antimony. It is an fifth group element. When you're adding group 5 elements as impurities, it will give rise to N-type semiconductors. So one example of group 5 element is antimony. Antimony is given by Sp. So antimony is given by Sp. Okay. So you see here, this is the replaced atom, and you know that germanium and silicon need only 4 atoms for establishing covalent bond. Silicon has 4 elements in the valence band, in the conduction band, outermost band. So they need 4 more atoms from the. If you have germanium here, these 2 atoms are paired. These two will be paired. These two will be paired, and these two will be paired. When I'm replacing this germanium atom with antimony, antimony has 5 electrons in the outermost band. So 4 electrons are bonded with germanium. 1 electron is excess. This excess electron will be contributing for the current. I have just shown one antimony atom here. So you know in a semiconductor you have 10 power between 10 power 7 to 10 power 28 electrons are there in a semiconductor, right? So if so many atoms are there, how many antimony atoms are there? You will think how many antimony atoms will be there, and all antimony will be giving one excess electron. When all these excess electrons are going to be formed, these excess electrons move in the conduction band and give rise to what is called as current. Okay, when you have excess number of electrons, that semiconductor is called as an N-type semiconductor. So N-type semiconductors have excess number of electrons. Very important thing you have to understand. Okay, so see here, I'm going to add a pentavalent impurity. Pentavalent means it is going to have 5 electrons in the valence band. What are the examples of pentavalent impurity? Arsenic, antimony, phosphorus. And these are called as group 5 elements. Why group 5? Because of 5 valence electrons in the outermost band. So when these 3 elements are added to silicon and germanium, the intrinsic semiconductor becomes N-type extrinsic semiconductor. N-type means it is having large number of electrons, and extrinsic means it is going to become impure. So see here, germanium has 4 valence electrons, antimony has 5 valence electrons. So each antimony atom forms covalent bond with surrounding 4 germanium atoms. So 4 electrons are being paired to form the covalence bond. And when the 5th valence electron is left free, that is not loosely, it is loosely bound. So the 5th electron is not bound to any atom of antimony or germanium, right? So this this 5th electron can be easily excited to the conduction band to produce current. So this 5th electron can be easily excited from the valence band to the conduction band, producing current. Very, very important type of intrinsic. We are not bothered because the conductivity is very poor, but extrinsic, you should clearly know what is doping, how much impurity I am going to add, and based on the impurity type, I have N type and P type. So when you add N type impurities, number of electrons will be more. When you add P type impurity, number of holes will be more. Okay. So see here, each antimony atom contributes 1 excess electrons without creating a hole, because out of 5 electrons, only 4 electrons are bonded. 1 electron is excess. So this antimony is donating 1 electron excess to the semiconductor. So since it is donating, this impurity is called as donor impurity, because it donates 1 electron for conduction. So this pentavalent impurity, whatever we are going to add, is called as a donor impurity, because it is going to donate 1 electron for conduction. So when it is going to donate 1 electron for conduction, donor atoms become positively charged because it loses 1 electron. Antimony has 5 electrons. It has lost 1 electron because of this adding the impurity. So it becomes positively charged. Okay, it cannot take part in conduction. Only the 5th electron given by this donor impurity will take part in the conduction. So when you add more number of pentavalent impurity, the number of electrons in the valence band will be very high, and these electrons will be easily moved to conduction band. When more number of electrons are there in conduction band, more current will be produced and more conductivity is obtained from the N-type semiconductor. So because of doping, more number of electrons are produced compared to the number of holes. And so in the N-type semiconductor devices, electrons are the majority carriers and holes are the minority carriers. Intrinsic semiconductor, number of electrons equal to number of holes. In an N-type extrinsic semiconductor, because each antimony atom is contributing to 1 excess electrons, the number of electrons are there is going to be very, very high compared to number of holes. So when electron population is very high, it becomes majority. So since holes are going to be minimum in number, it becomes minority carriers. Any doubt in N-type? Please ask doubt if you have in N-type. I am just teaching each topic and waiting for you to get clarified. That's why I'm giving this time between the topics, so that if you have any doubts, you can ask me then and there. Can anybody summarize what is N-type? Why do we go for N-type? Why do we go for extrinsic semiconductor first? Why? What is the need for going to extrinsic semiconductor? Why we go for extrinsic semiconductor?
To increase conductivity at room temperature
Very good. And how do we obtain that?
by adding impurities, by doping the semiconductor.
Yes, one type of impurity what we have seen is N-type. In N-type, what do we do?
We add a pentavalent atom like
Yes, pentavalent
antimony.
atoms are present in group 5 of your periodic table. So whatever element you take from group 5 and add the impurity, what happens? Yes. What
It,
happens if I add a pentavalent impurity?
it donates 1 electron and then it gets a positive charge, gets fixed in the lattice, and then the
Yes.
donated electron helps in
Where is
conduction.
the donated electron present?
So can you repeat the question?
Presence in valence band or conduction band? The donated electron, as you see in the diagram in your screen, it is present in valence band or conduction band. It is present in valence band only. Only when you apply energy, this loosely bound electron in the valence band will go to conduction band, causing current. So all these three electrons are there only in valence band because I have not applied any energy. Only when you apply energy, all these loosely bound fifth electron from the antimony atom will be going to the conduction band and producing more current. So that is the reason why you have increased conductivity in N-type semiconductors. And since you have more number of electrons produced in this process, electrons becomes majority carriers for N-type semiconductors and holes become minority carriers. Okay, holes become minority carriers. So that is the conclusion of N-type semiconductors. So N-type, remember, N indicates electron. So electrons are excess. So how to make electrons, how to get excess electrons? You have to add pentavalent impurity. And how pentavalent impurity provide excess electrons? Pentavalent means 5. Silicon and germanium need 4. 1 is excess. That is going to be the key element which is going to contribute to my conductivity. Okay, so this is N type. I hope N type is clear. I think now P type, you can make a guess. In P type, what should be the significance of P? I told you. What is meant by P? Where will you use
Holes.
P? Yes. So in P type, I am going to produce holes. What is hole? What is meant by hole? What is
When
hole?
electrons move from valence band to conduction band, the hole is created. So
Yes.
it
Or can I say absence of electron is holes?
yes.
Yes. Silicon and germanium need how many electrons in their valence band to form the covalent bond?
Four.
Silicon and germanium require 4 electrons to form the covalent bond. So if I make one electron short and the electron is not there, that becomes a hole, right? So in here, what impurity I should dope? In N type, we have to dope pentavalent impurity. Here, what impurity I have to dope? I have
Trivalent.
to, yes, I have to make one electron less. So silicon and germanium need 5 electron, the 4 electrons. So 4 minus 1 is going to be 3. So I am going to dope my semiconductor with group 3 elements or trivalent impurity. The trivalent impurity, one example is given boron. Boron is a trivalent impurity. Boron has only 3 electrons in outermost valence band. So 3 electrons will form a perfect bonding with the germanium atom, and one germanium atom will not have a electron to form the bond. So what will happen? This electron will jump here to form bond. So this covalent bond becomes unstable. So this electron will jump to stabilize this bond. Here you have a shortage of electron. This electron will jump to make that bond stable. So this electron will jump here. So it is just like when electron is moving from one bond to another bond, you have an absence of electron, you create hole. So when electron is not here, you create a hole. When electron is not here, you create a hole. So in this way, you generate holes in an excessive way by doping the semiconductor with trivalent impurity. Trivalent means group 3 elements. Okay, the same diagram, if you see the pentavalent, one electron is excess, but here one electron is in short. So to make this bond stable, the adjacent electron will try to come to this position to make this bond stable. When this bond is stable, this becomes weak. And here loss of electron. Loss of electron is going to be a hole. So in this way, we generate more number of holes. So see here, I am adding trivalent impurity. Example for trivalent impurity is aluminum and boron. So aluminum or boron is a trivalent impurity. Okay, so see, you need 4 bonds to make the atom stable, but one bond is incomplete, which gives rise to hole. So when a trivalent impurity is added, it increases number of holes in the valence band. So when you have large number of holes, the semiconductor becomes a p-type semiconductor, and the majority carriers in p-type is going to be holes, and electrons are going to be minority carriers. And see, and since this p-type semiconductor is going to it is not donating electron. It needs electron for stability. It is accepting the electrons, right? So it is called as acceptor impurity. It accepts the electron from the nearby atoms to form the covalent bond. So it is called as acceptor impurity. And since each boron atom is donating a hole for conduction, it becomes negatively charged. Donating a hole, when you donate an electron, it becomes negatively charged. It becomes positively charged. When you donate a hole, it becomes negatively charged. So since the holes are more and more and more holes are there in the p-type material, the majority carriers are going to be my holes and electrons are going to be my minority carriers. See how extreme type of devices we have in semiconductors. So one is n-type where electrons are dominating, holes are minority. And the conduction is mostly due to large number of electrons. In p-type, holes are dominating, electrons are less in number. So conductivity is mostly due to the holes. And I can choose which semiconductor I want, either n-type or p-type. So if you want n-type, dope with pentavalent impurity. If you want p-type, you dope with trivalent impurity. Example for pentavalent impurity, arsenic, antimony, phosphorus. Example of trivalent impurity, boron, aluminum, and other group 3 elements. You can refer to the periodic table. I hope you know what is meant by periodic table. It has a list of elements from number 1, atomic number 1 to whatever the last element discovered, right? So in that you will have a specific grouping called group 5 and group 3 elements. So those two categories are impure doping elements for me semiconductor. And what is group 4? Group 3 and group 5 are your impurities or your doping elements. What is group 4? What is group 4? How do they give the name? Yes, somebody told the answer.
Silicon and germanium.
Yes, silicon and germanium belong to group 4. So elements in group 4 are predominantly semiconductors, and on either side of group 4, group 3 and group 5, they are going to be our doping agents. So group 3, if I am going to dope, I will get p-type. Group 5, I am going to dope, I will be getting n-type. So any doubt in topics what we have seen so far? Conductivity we'll see tomorrow. So any doubt in the topics so far we have seen, you can ask. Now the class is open for discussion and doubt clarification. I don't want to give you so much information just in the second day of the class. That's why I'm going very, very slow, because you just need to have first a feel of the subject. Only then things become very clear to you. Okay. So any doubts and clarification you have, you can ask. And I'll be sharing the recording as and when I receive it. I think I mailed it yesterday. Did you get the recorded version link?
Yes.
Okay, fine. I have posted the textbook in your Google Classroom. I also posted the first part of the PPT, whatever I am taking in the Google Classroom. So if you are really interested, you can download them and even study in advance of the classes when you attend. So you can just go through what is there and you can come prepared for the class. I don't know how many of you will do that, but just in case for those who are very curious about the subject.